So this is a video about chapter 25, the electric potential, and we're going to relate the gravitational and electric potential energies. We're going to talk about and learn about electric potential energy, electric potential, and how we visualize the potential, the electric potential. So let's go back to force and think about gravitational versus electric force. And here on the left, we see that we know that the mass and the gravitational field determine the force. So if I have a mass and it's in a field, I see that my force points down. There's a force exerted on the mass. The field is the same, but if I have two masses and say M2 is bigger than M1, then the gravitational field is the same, but the force is going to be twice as big for the mass that's twice as big. And we have a similar analogy for the electric force. The electric force depends on the field and the charge. So they're analogous. We can think of the mass and the charge as the thing that's being acted upon, right? And the gravitational field in the electric field as the field that creates the force. So here we have the force on this charge is down because my electric field points down. If I have a charge that's twice as big, then my electric force will be twice as big. We also notice that here we're talking about masses. If we're thinking about the mass, then these two objects will not have the same force if we consider both electric force and gravitational force, because we have a mass that's twice as big. The electric force will be the same because the charges are the same. But when we think about the gravitational force, it'll be bigger for the bigger mass. So what about the analogy between gravitational and electric potential energy? Well, we know if we have a mass, right, that's a height above the ground, that our gravitational potential energy is mgh. And so if our mass is twice as big, we're going to have a bigger potential energy. And that's analogous to our electric potential energy. So electric potential energy, if I have a positive charge, I'm going to have a potential energy for a positive charge near a positive plate. And so I have this difference of charge, which creates a difference of potential. And this positive charge is going to have potential energy because it's going to move to the right. And that potential energy between the positive charge of the plate and the positive charge itself, it wants to move away, just like here my mass wants to move down. And so we have this potential energy. So we can think about this charge. When a charge is near the same charge plate, it's going to have a potential energy away. Electric potential energy is the work you would have to do to assemble a system of charges. So imagine if I have a charge, say Q, and I bring another charge, another positive charge towards that Q, right? I have to do work in order to bring that charge, that second charge, closer to the first charge. And so that is potential energy. So my potential energy of 2-point charges is K, Q1, Q2 over R. So that's the two charges are positive, so therefore I have a positive potential energy and I'm doing positive work. Let's look at this example. If I have a Q1, this is my source charge, and I have another charge nearby, Q2, and my charge moves away. My force on Q2 due to Q1 is denoted by this red arrow, and you can see when Q2 is closer to charge Q1, the force arrow is bigger, and when Q2 is over here, further away, the force is smaller. And so that just tells me that I have a changing force. So the force changes with distance away from my source charge Q1. And if I want to calculate the potential energy, that's the work, and the work is the force times the distance. And so this is my distance going from xi to initial position x to final position x. And I need to take the integral because my force changes, right? So since my force changes, I need to integrate because at each position of Q2, I'm going to have a different force. So that's what's going to go in my integral. And just again, remember that when I have 2-point charges, right, I have the electric potential energy is K Q1 Q2 over R. And if I had 3-point charges, then I would have 3 terms, right? I would be adding up the potential energy of Q1 and Q2, Q1 and Q3, and Q2 and Q3. So I would have the sum of the electric potential energy for the charges when I bring them together. Well, what about the unit of energy? And when we talk about potential and potential energy, we usually talk about volts. And for energy, for electric potential energy, we talk about the electron volt. And the electron volt is, the symbol is E. So E is for electron, right? And volt. And it's the energy required to move one electron through a potential difference of 1 volt. So 1 joule is really large when we're dealing with electrons, atoms, and molecules. So that's why we use this electron volt unit instead. And so what is the equivalence between electron volts and joules, right? Both units of energy. Well, 1 electron volt, we can just plug in the values for the electron, which is 1.6 times 10 to the minus 19 coulombs, times 1 volt, and we get 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. So looking here at these possibilities, right, which set has a positive potential energy? Well, we just said earlier that when I have a charge, so let's say I have this charge, positive Q here, and I bring this negative charge towards positive Q, my positive charge, bring this negative charge towards it, and say I start far away and I move closer to it. Oops. I don't have to do work. I don't have to push that charge, right? It's attracted because this charge is positive and this charge is negative. So I don't have a positive work. Same thing here, right? When I release this charge attracts the negative charge, so therefore I'm not doing positive work. But in this bottom example, I have to actually push the charge towards the other positive charge because they repel. So as you saw, this is the correct answer, and we could also look at it from the equation. So the potential energy is K Q1 Q2 over R, and both of my Q's are positive, and so that gives me, in terms of the equation, I have a positive potential energy. So in this case, looking at the equation, Q2 is negative, so I would have a negative potential energy, and this one I have a negative also. And these two are different because my R would be different, right? The R is less in I versus double I. So instead of potential energy, we're going to focus on the concept of electric potential. And electric potential is, we have a definition. So electric potential is represented with a V, and that's the potential energy of my sources then divided by Q. Right? So we've seen this before where we have the force, electric force, and we had the electric field was the force over Q. And that's when we were thinking about the force and the electric field, and they were vectors. And now we are now talking about electric potential energy and electric potential, and they are scalars. So similar to when we talked about force for kinematics last semester, and then we talked about energy. So we went from vectors to scalars, and we're doing the same thing here when we go from potential or force and electric field. Now we're talking about potential and potential energy, and these are scalars. So it's just interesting. Just remember that my potential is defined as my potential energy divided by Q. So sometimes we can say the potential is the potential to have potential energy. So I just know it's just a little play on words there. And the unit of electric potential is the unit of energy divided by Q. So the unit of energy is joules, and the unit of Q is coulombs. So that's where we get 1 joule per coulomb. My teacher always used to say, what is a volt? A joule per cool. Kind of an easy way to remember it. But 1 volt is equal to 1 V, and it's just 1 joule per cool. And batteries are labeled with different potentials. So AA, C, and D batteries all have 1.5, are all at 1.5 volts, meaning the voltage, if we measured it from the positive end to the negative end, we would read the voltage on a multimeter as 1.5 volts. That would be the potential difference between the ends of the battery. And so just thinking about that, I have a lot of positive charges here at the positive end and negative charges here at the negative end. And so I'm measuring that potential difference. So I always have a potential difference when I have positive charges in one area in space and negative charges in another. So understanding potential difference. We can think of the analogy with gravitational potential energy, where the object with positive potential energy will fall if released. So here, looking at this positive charge, if I bring that positive charge close to the positive plate and I let it go, I know it's going to move to the right. So when it's released, it's going to move to the right. So I know if I do that, that has potential energy. That if it falls towards the negative plate, moves to the right when I let it go, then it has positive potential energy. And I want to think about potential, that having a positive potential, means it's more positive on this side, than the other side. So it's more positive here. And whenever I'm thinking about high or low potential, positive to negative potential, I want to think about a positive charge. So if a positive charge would move from left to right, then the left side is at high potential and high potential energy, and the right side is low and low potential energy. So positive charges move from high to low potential. Well, what about negative charges? So unlike mass, charge can be positive or negative. Thus, the potential energy depends on the sign of the charge. And so just think, where does the negative charge, where when I let the negative charge go, where does it move away? So here my negative charge is going to move away from the negative plate. So if I let it go right here, it's going to move to the left. So that tells me that I have high potential energy here. It's like at the top of the mountain. And then when I let it go, it's rolling to the bottom of the mountain, and it has low potential energy at the bottom. So for negative charges, they move from low potential to high potential, right? So they move, this is a low potential because it's negative. This is at a higher potential because it's positive. And so negative charges move away from low potential, away from the negative, and they move toward the positive. So we'll talk about conservation of mechanical energy. So a charged particle moving through a change in electric potential will speed up or slow down such that it conserves mechanical energy. So remember that mechanical energy is 1/2 mv squared. So it's the energy of its movement. So that's just saying that if I have a charge and it's moving, so it has a velocity, that it's going to either speed up or slow down to conserve that energy. So it starts out with a velocity, and it moves through, in this example, it's moving from a higher potential to a lower potential. It's going to speed up because it's, say, more positive here and more negative here. So it's going to move to the left, and its speed is going to increase. Whereas here, if I have so higher potential means it's more positive over here somewhere, then this charge is going to it's moving, it has a high velocity, it's moving to the right, but it's going towards a higher potential, or going towards something positive. So that means it's going to slow down, right? So we can represent that with our conservation of energy equations. And this just is saying that my final kinetic energy plus my potential energy, my electric potential energy, is equal to my initial kinetic energy plus my initial potential electric potential energy. So just like we would have Kf, right, 1/2 mv squared is Kf, plus here we might have mgh, right? So think about like going up a mountain or going down a mountain. But here instead we're thinking about that with potential and with electric potential energy. Okay, here we have a electric potential energy problem. We have a proton, so positive charge with a speed of 2 times 10 to the 5th meters per second, enters a region of space in which source charges have created an electric potential. What is the proton's speed after it moves through a potential difference of 100 volts? And what will be the final speed if the proton is replaced by an electron? So we're going to do the proton first. So let's see, we know that A is going to be find the velocity final of a proton, and B is find the velocity final of an electron. We're given we know, I guess it doesn't tell us, but we should know or look up the charge of a proton. So Q of a proton or an electron is equal to 1.7 6 times 10 to the negative 19 coulombs. And the mass, since we can see we're calculating, we're doing potential energy, and it has an initial velocity, we know we're doing kinetic energy. So we know we need to know the mass of a proton. And a proton mass is 1.67 times 10 to the negative 27 kilograms. That's the mass of a proton. Let's see, what's the mass of an electron? Let's see if I look up mass of an electron. So the mass of an electron is equal to 9.1 times 10 to the negative 31 kilograms. That's for part B. Is there anything else we need to know? No, I think that's it. Okay, so what we want to do is we want to use the conservation of energy equations. So I'm going to say K initial plus U initial is equal to K final plus U final. And so so the other thing I need to think about is what's going on here, right? And if I look here, if I look right here, this tells me that my proton is going pretty fast in the beginning and then slows down. So it's going to be going faster at the beginning than at the end. So if I want to like draw that, my model for the potential difference is I like to think about plates. So I'm going to say that I have this plate here and a plate here. And how is a proton, a positive charge, going to slow down? If it goes into this area between the plates, it must be going from a high potential or a low potential to a high potential. So that means it's going from the negative side to the positive side, because that's what's going to slow it down. As a positive charge in here, right, this Q, as that goes this way, it's going to slow down because it's getting closer to this positive plate. And so that means that I'm going to have a potential energy of Q times V. So here I'm starting at 0 volts and I'm going to 100 volts. So when I start out, I have no potential energy at the start when it first enters. So this is going to be equal to 0. But I do have the terms for the rest of this. So let's see. Okay, so I'm going to have 1/2 mv initial squared is equal to 1/2 mv final squared plus the potential energy is Q times V final. Okay, and so looking at this, I know that I'm slowing down, so I actually know that this is going to be, instead of a positive, it's going to be a negative. I'm sorry, that's not correct. It's going to be a positive value. So this is a positive value. This just means I have a final kinetic energy, so a certain energy, and then plus a potential energy. So I'm slowing down and gaining potential energy. So as I move to the right, I'm gaining potential energy as I get closer to the positive plate. And I'm looking for this velocity. So I'm going to rewrite this equation as 1/2 mv final squared is equal to 1/2 mv initial squared. And I'm bringing this term right over here to the other side. I'm just subtracting from both sides. Minus Q times V, the potential final. Right, so this is a capital V here, and the velocities are little v's. And I'm looking for this. This is what I'm solving for. So I'm going to multiply every term by, I'm going to multiply by, or divide by 1/2 m. So I'm going to divide this by 1/2 m, divide this by 1/2 m, divide this by 1/2 m. So that cancels, this cancels, and I'm left with V final squared, the velocity squared, is equal to, this cancels too, is v initial squared, the initial velocity squared, minus q times v, the potential. Let's make that a capital V so you can really tell they're different. V final, potential final, and then I've got bringing the 2 up to the top over the mass. And so V final then is equal to the square root of V initial squared minus 2q over m potential final. Okay, so plugging in my numbers, I'm going to have V final is equal to, let's see, 2.5 times 10 to the 5th meters per second squared minus, let's move over a little bit, minus 2 times 1.6 times 10 to the negative 19 over 1.67 times 10 to the negative 27, this is kilograms, and this is coulombs, times 100 volts. Let's go over like that. So let's erase this and just be a little, all right, that's volts. And so when I multiply that through, I get V final for the proton is equal to 2. What did I get on MATLAB? 2.1 times 10 to the 5th meters per second. So what happens, that's part A, so that's my answer to part A. And part B was find the velocity if my charge is, let's see, move up just a little bit. So now what about the electron? All right, we'll do an electron. So what happens is my Q is different and my mass is different. So here my V final, my equation is going to be V final, the final velocity is equal to V initial, same. And now instead of a minus, I'm going to have a positive. So I'm going to have plus, right? Because my Q is or let's leave it as minus. Actually, let's leave it as minus. And we'll say minus 2 times a negative Q, right, over the mass of an electron times the potential difference. Final. So my numbers are all going to be the same, except I'm going to have V final is equal to, I know I'm plugging in 2.5 there, so I'm just going to have V initial squared plus 2q over the mass of an electron times V final. All right, let me do the math there. So let's see, I think my mass is different. So my mass is, I'm just entering this on in MATLAB, 9.1 e to the negative 31. 31. Okay, so then V final right. Okay, so when I plug the new numbers in, I get that V final for an electron is equal to 5.9 times 10 to the 6th meters per second. So that's for an electron. So this is an electron, and this is a proton. Okay, so this is about the electric potential of a parallel plate capacitor. So one of the great things, if you remember from Gauss's law, we learned that the electric field is constant for a plate, for a plate of charge or a sheet of charge. And so what that means if we have a constant electric field between two plates. So look at this example, and we can see we have a positive plate on the right and a negative plate on the left. And so these little light green slices are not real. They're like imaginary. We're just imagining what the potential is at those places. But the gray sheets are like sheets of charge. And so what we can see is that we have equipotential surfaces in these light green sheets. And what that means is it just means that everywhere along this light green sheet, I'm going to have an equipotential surface, meaning it's everywhere along there is at 1 volt, right? And then if I move to the left a little bit more, my potential is decreasing. And everywhere on this sheet, if I could measure it, I'm going to have 0.5 volts. So that's really interesting that's an equipotential surface, meaning it's constant voltage on the light green sheet. And also notice that I have a positive plate, say 1.5 volts, like the end of a battery, the positive end, and then the other end of the negative end of the battery is negative. And so I have decreasing potential. So I start from 1.5 volts to 1 volt to 0.5 volts and to 0 volts. And I can represent that, right? If I have volts per distance, and this distance is from here, the positive plate to the negative plate, I can see that my voltage changes along this distance, right, in a linear fashion. So if this is my negative plate, here, if I start here at the negative plate, and this is my distance is equal to 0, or s is equal to 0, or say x is equal to 0, and I move to the right, this is my voltage at that location. And then if I move to the right some more, this is my, at 2 millimeters, this is my voltage, right? And then if I move to 3 millimeters, I'm going to be at the positive plate. And I can also look at it like this, right? So I have the negative plate at 0 volts, and then I have the positive plate at 1.5 volts. And you can see that I have just a dotted line kind of to represent, imagine looking at this case on the left from directly on. I would see like this surface, right, goes in and out of the page. This surface goes in and out of the page. And I can also think about it like this, like imagine I'm like climbing a mountain, right? So the bottom is here. This spot right here is this spot. This spot right here is here. And then I'm at the positive plate right here. And so remember that positive charges, they want to move from high to low potential. So positive charges are going to start at the positive plate. They're going to want to move to the left, or they're going to fall down this hill or fall down this hill. So this hill is like this, or like that, or like that. Positive charges move to the left, whereas negative charges want to move from low to high potential. So they're going to want to get away from the negative plate. So they're going to want to move to the right, or negative charges are going to want to move up the hill, or they're going to want to move this way. So electric potential, like the electric field, is an intrinsic property of the charge. And so that just means, right, if I have charges, we know that in space there's going to be an electric field, and there's also going to be an electric potential. So if I have charge, I have electric potential. And so for a point charge, my electric potential is the electric potential energy divided by Q. So that just gives me 1 over 4 pi epsilon naught Q over R. And remember, this is just K. So potential is just K Q over R. And so the potential exists at all points in space if there's charge present, but it approaches 0 as R goes to infinity. So what does that mean? It just means as R gets bigger and bigger, V, the potential, gets smaller and smaller. And we can look at that with a graph, right? So my potential versus position decreases with increasing R when Q is positive. If we think about it too, the magnitude of the potential gets smaller and smaller. And if I have a negative Q, so if I have a charge that's negative, I have potential also. The magnitude goes towards 0. And here the potential is going to be negative, a big negative number for a negative charge. And then it's going to be a smaller and smaller and smaller negative number as R goes to infinity. So if we don't want to visualize electric potential, right? So just imagine it's an imaginary surface you're thinking about. But what I can think about is for this equation, V is equal to KQ over R. I can think about it as like these equipotential surfaces. So just imagine like spheres around my charge. And at everywhere along this sphere, right, my potential is the same. So I pick this outside sphere. Everywhere along there, my potential is the same, which makes sense because I'm the same distance away from my charge. I'm 1 over R, R away. And then this here, right, is the same as an equipotential surface, and then all the way inside. And so I can see that inside, my potential is going to be much bigger because R is much smaller. And then all the way out here, my potential is going to be lower because my R is bigger, so my potential is going to be smaller. And I can also draw this as, imagine that the charge is like the peak of a mountain, and as I move away, I'm going to have an equipotential line here, and then a little bit further out and a little bit further out, and each of these dotted circles represents a place where the potential is equal. And I can think about it like this too, like an elevation graph. So the closer I am to the charge, the larger my potential, and the further away, right, the smaller my potential. And so I can use all of these, the potential graph, which is this one, equipotential surfaces, which is this one, my contour map, or my elevation graph. And they all are visual representations of potential. So they're all correct. And it's just thinking about and understanding them and being able to relate them and what makes most sense for the model in your head about visualizing electric potential. So what do we do when we have more than one charge? Well, we can it's an easier process than calculating the electric field because potential is not a vector. So just like energy, right, when we were calculating energy, 1/2 mv squared, when we were talking about that in the first semester and how energy is a scalar, potential and potential energy are scalars. So when I want to calculate potential, so if I have these two charges, right, each one has potential. Just like we saw over here, right? If I have a charge, I have potential. But what happens when I have more than one charge? Well, they both have potential, and I can just add them up at this spot. So if I want to know the electric potential of the positive 2 nanocoulomb charge, I can calculate it. If I want to know the potential of the negative charge here, I can calculate it at this spot. And then to find the potential at that spot due to both, I just add them up. That's what the sum means. So however many charges I have, I can calculate the potential at the point that I'm interested in. I pick it, point P. I calculate it for each of them. At this point, what does this contribute? At this point, what does this contribute? And then I add them all up, and that gives me my net electric potential. And just remember that my potential is a scalar, right? So all I have to do is add them up. Okay, in this example, I want to calculate the potential of two charges at this point P up here. My pen turned off for a sec there. Okay, so this is my point P. That's my point P. And I'm trying to find the potential V at P. And what do I know? Well, I'm given that, we'll call this one R1. This is my R1 equals 5 centimeters. That's just such bad writing. So let me fix that. So this is going to be R1 equals 5 centimeters. This is going to be Q1. This is going to be Q2. And we'll say this is R3, or R2, sorry, R2. And so I know that the equation for potential is V is equal to the sum of all the charges I, so I have 2 in my case, Q I over Ri. And that just means I'm looking at each of the Q's and I'm plugging in. So I can write that then as V is equal to, the potential is equal to K times Q1 over R1 plus K times Q2 over R2. And just so I don't have to write out K all the time, I'm going to write V, the potential, is equal to K Q1 over R1 plus Q2 over R2. And I'm going to plug in my numbers. K is 9 times 10 to the 9th newtons, meters squared per coulomb squared. And let me move over just a little bit. Times Q1, which is 2 nanocoulombs, so that's 2 times 10 to the minus 9 coulombs over 5 centimeters, which is 5 times 10 to the minus 2 meters, plus a negative, let's move over a little bit more, a negative 1 times 10 to the negative 9 coulombs over 4 centimeters. So 4 times 10 to the minus 2 meters. And let's see if I bring that back. So then when I plug that into my calculator, I get the total V is equal to 135 joules per coulomb. And we can see if that makes sense for our units. So if I have Newton meter squared per coulomb squared times coulombs per meter, I get a Newton meter, because I get 1 meter left, right? So I just get a Newton meter, and a Newton meter is the same as, let's see, so what is a joule? So a joule is, the units are a Newton, let's back up for a second. So joule is a kilogram meter squared per second squared, right? How do I know that? Well, it's mass, so 1/2 mv squared. The mass is kilograms. The velocity is meters per second, so meters per second squared. And coulomb per meter. Yeah, okay, so I still have a coulomb, I think, down here. So I have a squared. So I have an over coulombs. Okay, so then if I think about, let me move this down a little bit, about my volt. So this is a volt, right? And this is my my joules. So how can I write joules? Joule is equal to a Newton, right? So what's a Newton? A Newton is a kilogram meter per second. So a joule is a Newton, this is squared, a Newton times a meter, right? So if I want to then substitute in, so a volt then is a Newton meter, which is a joule, over a coulomb. So that's how we get the units. So this is my final answer. There we go.